Let us prove that a to the power x is greater than x to the power a whenever x is greater than a and a is greater than e. Time and again you might have come across cases like which one is bigger, is 3 to the power pi is bigger or pi cube is bigger, or like 40 to the power 41 is bigger or 41 to the power 40 is bigger. What does this say is that if you take higher power, then the number that you get will also be bigger whenever both the bases are greater than e. Let's prove it. We want to show that a to the power x is greater whenever x is greater than a and a is greater than e. Now we see that x is the power or the exponent. So that reminds us about something like exponential function, and we know that exponential and logarithm are inverse to each other, and e to the power log of y is simply equal to y whenever y is greater than 0. So let's apply this result. So let's replace by a to the power x by e to the power log of a to the power x, and x to the power a by e to the power log of x to the power a. Of course, both are having base to be e. Both of the logarithm are having base to be equal to e. Now we know that powers can be taken out of the logarithm. This power x, we can take it out of the logarithm. So does this power a. So this inequality is true if this is true, because those two numbers are same, or if we can take powers out of the logarithm. So we can write this as e to the power log of a x times log of a, that is greater than e to the power a times log of x, of course with base e. Now you see that we got the same base. Now e to the power x has a property that if x is greater than y, then e to the power x is greater than e to the power y. It's a simple result, like for example 2 to the power 10 is greater than 2 to the power 8, that's greater than 2 to the power 5, that's greater than 2 to the power 1. We just take higher power, then the number that we get will also be higher. If we take bigger power, then the number that we get will be bigger. So if x is bigger, then so does e to the power x. Let's prove it this one as well. So we will apply calculus. What we claim is that fx equal to e to the power x is strictly monotonically increasing function. Let's prove the claim. We have fx equal to e to the power x. So we will apply calculus. In particular, we will find derivative of fx. F dash x equal to d dx of e to the power x, and that's simply equal to e to the power x, and we know that e to the power x is greater than 0. So if e to the power x is greater than 0, and so derivative of a function is greater than 0, then we know that function to be monotonically increasing. So we have shown that fx equal to e to the power x is a monotonically increasing function. In other words, if I take higher power, then the number that will also be higher. So it is sufficient to show that x times log a is greater than a times log x. That is, let's take this quantity to the left hand side, x times log a minus a times log x, of course with base e, is greater than 0. Now is that true? Oh, we don't know. Let us define another function hx. Let hx equal to x times log a minus a times log x. Then what can we say about h? Is it monotonically increasing? Is it monotonically decreasing? Of course, when I say log of a number, then x has to be greater than 0. Of course, we are already assuming x greater than e. So what can we say about h dash x? Derivative of x with respect to x is just 1. log of a, we are assuming a to be a constant, minus a times derivative of log x with respect to x is just x. Therefore, h is monotonically increasing if h dash x is greater than 0. But h dash x is greater than 0 if log of a with base e is greater than a by x. Now we are assuming x to be positive, so we can multiply by x. And we are given a greater than e, so log of a with base e is greater than 1. So I can divide by log of a with base e, inequality still maintained. So if we choose x greater than this quantity, then we are assured that hx equal to this is a monotonically increasing. Now we observe that log of a with base e is definitely greater than 1. Log of a with base e is greater than 1 since a is greater than e. Therefore, a by log of a with base e is less than a. It is smaller than a. So we can say safely that h is monotonically increasing. Therefore, so we can say it safely that h is strictly monotonically increasing for x greater than or equal to a. We found h dash x to be positive for x greater than or equal to a by log of a, and a by log of a is definitely less than a. It is definitely less than a. So it is strictly increasing for all x greater than a by log a. In particular, I can take x greater than or equal to a. So h is strictly monotonically increasing for x greater than or equal to a. Therefore, for x is strictly greater than a, h of x has to be strictly greater than h of a. Now let's write the value of h of x. We have defined h to be hx is x log a minus a log x. So x log a minus a log x, that's the definition of hx, is strictly greater than h of a. If I write x equal to a, then I get a log a minus a log a. Oh, that's just 0. Of course, with base e. So we conclude that x times log of a is strictly greater than a times log of x, and we are done. We can, if you are not convinced, then you can say that, well, fx equal to e to the power x is monotonically increasing function. So if I take higher power, then the number that we get will also be higher. So e to the power log of e to the power x times log a has to be greater than e to the power a times log x. Again, powers can be taken out of logarithm, so the reverse is also true. So we can write e to the power log of a to the power x is greater than e to the power log of x to the power a, and again e to the power log of y is simply equal to y. So we can write this as a to the power x is bigger than x to the power a whenever x is greater than a and a is greater than e. And so we are done.